Good morning, this is Dan. Over the next few days, I'm going to be preparing one or two presentations on some of the science I've had the privilege to work on. Today, we're going to talk about scanning electron microscopy. My history is analytical chemist. I'm an ex-research center director in this field of science. My primary research focus was XRD, which is an instrumental technique. SEM is what we're going to be talking about today. I've done a lot with elemental and forensic analysis and done a whole lot of work in the laboratory with catalysts. Those are all characterized by the above methods. My experience with instrumentation runs from ion trap mass spec to FT-NMR, which is the chemical version of what you would call an MRI. Familiar with XRF, XRD, fast atom bombardment mass spec, and SEM. And plus there's a whole bunch of other career. My past experience has been in industrial hygiene. I was a field chemist and an IH manager. What I did was I provided training to lab technicians in spore analysis and laboratory procedures. I drafted and implemented a corporate-wide QC and QA training manual to ensure a consistent knowledge base for all technical personnel. I served as a lead industrial hygienist at various petrochem facilities here in Southeast Texas. I supervised and trained field technicians in our 5 branch offices, and I prepared all reports before the owner of the company, who was the CIH, would sign off on them. In order for them to hold up in court or in an industrial background, you have to have a CIH signature. I also led a design team of engineers in implementing Phase 1 and Phase 2 site assessments. These things have sort of been downgraded over the last few years to Phase 1 and Phase 2. Before that, I was a QC QA specialist. We tested and implemented ISO 9001 procedures. We conducted testing and certification of medium voltage switchgear and generator control for the petrochemical and offshore marine industry. And I'm a certified teacher for chemistry and physical science. My academic credentials: engineering from Lamar. That's out of the Department of Civil Engineering, and I hold a BS degree in chemistry from the University of Texas at Austin. The SEM, the scanning electron microscope, there are several vendors of these instruments. Each one has their plus and minuses. The university that I worked at, we settled with Hitachi. They're up and coming. All their electronics are made in-house. Their tech support is second to none. And it's fairly modern, and it's a fairly compact instrument. The price, when you start bolting on the accessories, the price can explode on them. But just for the SEM and the EDAX, which is the elemental analysis, you're looking at about $100,000 or $150,000 for the whole system. It's really not a whole lot. It's sort of like financing a house. Instead of getting a mortgage payment, they use a research grant to pay for it. But there are some private companies that actually have these in their own basements. They use them for asbestos monitoring and some stuff like that. So it is conceivable for a private citizen to buy one of these, because all you need to run it's 120 electric power. There's a 208 3-phase that goes into it, but there's no water requirements. There's no water chiller. There's no fancy radiation shielding. All you need is basically a breaker box and a dedicated line. The 120 wall currents for the vacuum pumps, but the 208 3 phases for running the microscope at people's homes are 220, 240 volts, so it's no big deal. Pretty much with any modern day instrumentation, everything is done on computer and with push buttons. If you look at this instrument here, there are basically three buttons. There's a button you push that activates the high vacuum. There's a power switch, and there's an air switch that airs out the chamber. Pretty much everything else is driven by the computer, which is a Windows XP PC. So in theory, anyone who understands how to run a PC can operate the instrument. Unfortunately, this this technology drive towards just using computers has phased out a lot of jobs, including eventually mine. Back in the old days, you used to have a PhD and a team of engineers and electronics gurus around you to run one of these instruments, but now I can pretty much train any middle schooler who can operate a PC to run the instrument. Now, getting publishable data and being able to explain what's going on is a totally different ballpark. That's why I was hired and not a high school graduate. But in theory, just to run the instrument to get a picture, I can pretty much train a 10-year-old to do it. The SEM is the 3400N. That's just a model number. Basically, when you look at it, there's a trackball for moving the stage around. Your sample goes in this chamber. You have a movable aperture that's adjustable. The column is the magnetic column, and there's an electron gun on top that shoots the electron beam down that column of magnets. We'll get into this later. There is no radiation hazard or electrical shock hazard. Everything is pretty much safety interlocked out. If you open the chamber, you can't hurt yourself. This is a picture of the actual sample holder. It's a combination of stainless and copper. The inside the SEM has to be kept clean. Basically, it's a series of worm drives and computer control that enables you to tilt the stage X, Y, and Z, and you can raise it up and down, and you can tilt it. There are many different sample holders. This is the most common one, the single stub. There is a 33 stub multi-sampler that lets you do multiple samples. This comes into play almost every day when I'm running multiple samples. There are modified sample holders for drill bits, circuit boards, stuff like that. If you go to Austin, Texas, the Hitachi SEMs are in a lot of the major semiconductor vendors, and they have these robots that essentially cycle these wafers in and out of these chambers, and they do analysis for failure. First, we're going to give you a little primer on how optical microscopes work. The resolution depends on wavelength. For any optical lens system, that's around 400 nanometers, which is in the ultraviolet wavelength. There are some other advanced techniques like confocal that will lower this number, but we're not going to talk about those today. They're just too complicated, and that's a totally different subject. Now, the resolution for an electron microscope strictly depends on the acceleration voltage. For our microscope, the beam energy is 30,000 electron volts, so the theoretical resolution I can see is 0.5 nanometers, but resolve 5. We'll talk about that later too. I use the de Broglie equation to get this E equals hc over wavelength. It's a real simple physical approximation. I know some physicists may come in and argue that with me, but that's a pretty simple way of ballparking what the resolution should be. And the key takeaway here is on the electron microscope, it uses magnets instead of glass or plastic optics. The SEM is the scanning electron microscope, as it's commonly called. It's probably the most common instrument when it comes to electron microscopes. When you get to transmission scopes, the prices go up to several million. These are in the $100,000 ballpark. They even do have a desktop one that's less than that. The way it works is instead of using light, it uses an electron beam to scan the sample in a raster pattern. It's just like scan lines on an old TV, left to right, left to right, left to right. You can use it for pretty much any solid materials with very little sample preparation. In my slides, you'll notice I color code them. If it's in green, it's something that is easy to work with. If it's in red, it's something that's either extremely technical or it has some hard stops on it. Your sample may degrade depending on the voltage and duration. Like if I were to put a live sample in there, like a blood sample or a virus or a leaf or a section of a plant, it may degrade. But there are ways to get around that. The electron microscope has two modes, high vacuum or variable pressure. You use variable pressure for living things, or once was living things. If you have material that is an insulator, it'll charge. You use variable pressure. I tend to avoid this mode because I've figured out a way of doing it consistently without using the VP mode. Anytime you see a system that's high vacuum, you have to keep it clean. And you have to be real careful on what you're doing because when these systems break, they are very expensive to fix. Sample considerations, I can pretty much put anything in there. The sample has to physically stick or clamp onto a specialized mount. The sample cannot exceed the plate diameter, and it can't be too tall, because if it's too tall, it'll physically crash into the detector. It's mounted on the scope. So they give you a little ruler to measure your sample, and then you can set a height where it stops. It's really no different than a physical stop on a standard optical microscope. I can use any powder just as long as they stick to the carbon tape, and it can't currently be outgassing any liquids. You can't use the liquid or sample with volatile components because you can't pull a vacuum on something that's outgassing. They do make specialized liquid cells where you can actually put a liquid inside the SEM, but you have to go back to Hitachi and buy one. In our lab, not many people request this feature, so I did not purchase one. Basically, it's a sample holder that has a O-ring in it. If you have a material that's an insulator, it may charge, so you have to sample fast. Okay, what happens when an electron beam strikes a sample? There are about 10 different processes that happen at the same time. Each one of these is a PhD. Some of these measured properties have gone through to get people the Nobel Prize. Like Einstein got the Nobel Prize for the photoelectric effect. What happens is energy out. You get backscattered electrons, which is something that we're going to use. It'll generate an X-ray. You can use that for elemental analysis. You can generate a secondary electron. This is used to generate a flash of heat, flash of visible light. Bremsstrahlung along is background radiation. You've got to have a pretty strong beam to get an X-ray produced by it. In theory, it makes an Auger electron, but due to the fact that it's not a high vacuum system and other technical difficulties, these are not measured by a microscope. If the electron beam has enough energy, it'll go right through the sample, called a transmitted electron, a TEM. And sometimes the electron gets diffracted, so you can sort of do an XRD inside the instrument. In the microscope and the work that we do, there are only really three things that are measured. The secondary electron emissions give you an image, backscattering will give you an image, and X-ray emissions will give you the elemental analysis, which is the EDAX system that's mounted on the microscope. The Auger photoelectron, good luck finding that. The vacuum's not high enough. The mean free path is just isn't there. And also the EDAX silicon detector physics prevents it. They do have specialized instruments for doing Auger spectroscopy, but they're extremely expensive and a very high vacuum. They are a nightmare to work with. Okay, on the microscope, what parameters can you adjust? You can choose different detectors and the different vacuum modes. These are push button things. You don't actually manually swap a detector anymore. You push a button and it switches it. Same thing for the vacuum setting. It either establishes high vacuum or it doesn't. You can change the acceleration voltage. It's not dangerous to you, but it can really mess up your image. If you don't know what you're doing, this can lead you to results that are not usable. Same thing for the probe current, which is just the size of the beam spot. If it's too big or too small, you have issues. And most critically, if the aperture and the beam's not aligned, your images are not usable. You can adjust the astigmatism and focus without any real problems. And the magnification, which is this a field of view ratio, and the scan parameters, you can pretty much change at will. Now on the instrument, it does have all these auto functions. The auto functions are designed for the non-scientist to operate the instrument. I find sometimes they work, sometimes they mess it up to the point where I'm spending 4 hours realigning the aperture because the auto adjust just takes it out of range. I do everything manually on the instrument. That's probably one of the reasons why I got over a dozen publications. You can't fast track or rush science. Anytime I hear fast and easy analysis or record or breakthrough in this, I run for the door. The White House is finding that out with the coronavirus testing. They chose to spend 10 on the system, and they should have spent 100 on state-of-the-art PCR. Now they're paying the price because their accuracy is only 50%. So anytime I hear fast, accurate, cheap, revolutionary, brand new, anyone can use it, I start running for the door. Now, secondary electron. This is a extremely important thing for the electron microscope because I would say about 80% of my images are these. You remember in high school when they talked about valence electrons? They're the outside electrons that aren't bound real tight. What happens is when the electron beam strikes a sample, it kicks out these valence electrons, and those are what are measured. And they come from roughly 5 nanometers deep in metals, 50 nanometers deep for insulators. Anytime you're doing secondary electron work, it is sensitive to charging. I'll show an example of it later with a picture. If you have an insulator, you usually have to coat it with gold or osmium or do something with it. We had a gold sputter coater and it worked well. The kinetic energy of these electrons is 50 eV. 9% of them are more 10 eV. What you got to understand is on that microscope, even when I crank the beam energy down to the lowest settings, it's still several hundred orders of magnitude stronger than this. The minimum beam energy I can use on a microscope is about 1000 keV. So you're already putting in too much energy than the energy that's coming out, and that does produce a problem. That's why you want low energy settings for the acceleration voltage and a very, very small beam spot. What it's used for is what I would take away from the slide is that it's great for high-res surface mapping. And you'll see what I mean when I show you some pictures. The SE detector, it's based on Einstein's photoelectric effect. The way it works is the electron beam strikes a sample. All these physical properties are happening, backscattering, secondary emission. In a secondary emission, the electrons fly off the sample. They go into the scintillator, which is a sodium iodide crystal. When that electron strikes that scintillator, it gives off a flash of light. So you have an electron to photon conversion. That electron goes down a fiber optic pipe, goes into a multiplier tube, which is a night vision intensifier for our fans that are gun owners. The night vision takes very low light and it just amplifies it. Most of them have multiplier tubes, or at least the more expensive ones do. And what happens in the multiplier tube is that photon is converted back into that gets kicked up to extremely high flow, and you're able to measure current, and from that you're able to generate an image. I'm skipping a lot of the physics and details on this. These parts are extremely robust. You really can't burn them or fry them. They are high voltage. There is 10,000 volts across this scintillator section, so you have to be careful. How does a multiplier work? It's based on Einstein's photoelectric effect, where he got the Nobel Prize. The way it works is when a photon goes into this tube, it strikes these electrodes and it generates an electron cascade. The key takeaway here is one photon in generates 10 million electrons. When you have this many electrons, you can measure a current and generate an image. So it is highly sensitive. It is so sensitive that if I were to take this part out of the instrument, just radiation from space enters the instrument chamber and causes a current to flow, and you'll see some noise. And even if I put this thing in a totally dark room, there is some dark current noise. So there always is some signal being generated in here. These multiplier tubes are not expensive. We get into the Gen 4 and some of the newer stuff, it can get quite pricey. Backscattering, how does it work? The way it works is the electron beam strikes a sample, it recoils off the nucleus, and that electron strikes a detector. It's a fully elastic process. It's called, all it is the beam electrons scatter off the nucleus, and they strike that detector at different energies. Technically, the only thing that changes is the direction of velocity. There's a slight change in momentum, slight mass change, but the velocity vector changes. The takeaway from the slide is it is highly dependent on the atomic number. As you know, no two elements have the same atomic number. Right? Hydrogen's 1, helium's 2, helium's 3. Right? Lithium's 3, carbon 6. It just depends on the number of protons you have. The more protons you have, the stronger the backscattering signal. And we can use that to produce an image, which I'll show you in a few of the pictures. The backscatter detector is just a semiconductor wafer. What happens is when the electrons strike that silicon wafer, It generates an electron hole pair, and they get swept to an opposite pole by an applied bias, which is a voltage. Charge is collected and input into an amplifier, and it's positioned directly above the specimen, and it uses the output from the amplifier to generate a signal. But it's solid state, so you pretty much cannot harm it or degrade it. There's no need to replace it. Backscatter mode. What do you use it for? It's less sensitive to charging. You can use it for variable pressure mode if you do not or cannot afford a coating machine. Ours coats gold and platinum. Some of the other ones would do other elements. All it is a cold plasma. It's used for samples that have varying composition because the signal changes with the increase in atomic number. The main takeaway here is it gives you compositional information. Factors that affect image quality. A lot of times I'll submit my work to my research crew and my professors on campus, and they go, well, why is the image fuzzy? Or they tell me the microscope will evolve down to 5 nanometers and you can only go so high. Well, what you got to understand is you get what you pay for in these instruments. The main difference is if there's any external DC or magnetic fields, it has a problem. Vibration, acoustical noise, if someone's walking down hallways when you're doing a high magnification run, the image is susceptible. If the AC compressor kicks on or someone throws on the light switch or a motor or breaker is turned on, star capacitor, stuff like that. If your aperture is poorly centered or needs replacing, and this is probably the most common one. Charging the sample, that's not an issue because I code. Astigmatism is when the beam spot's not perfectly round. This is what separates the big boys from the small boys on the microscope end. When you get into these multiple corrected microscopes, you're talking well over 1 million compared to 100,000. You really can't do much with the astigmatism. All you can do is change out the aperture and keep it clean and try to center it the best you can. But the size of the beam spot really depends on how the magnetic column's set up in the microscope, and that's on the manufacturing end. You just can't go in there and fix it. You just can't buy an add-on that'll fix it. The most overlooked image quality impairment I find is the operator not understanding how a histogram works, and when you get into the auto mode where you're just clicking buttons and really not knowing what you're doing. I find a lot of the students that use the microscope don't have any background with standard photography, and this last one is very, very important if you present data based with a backscatter image. Probe current, all that is the size of the beam. If you're doing high magnification work, you have a very low current. For low mag work, it's a high current. If you have something that charges or non-conducting, you want to use a beam with a current of low energy and spot size. And next we're going to talk about conventional optics, so you understand how the physical optics of the electron microscope actually works. I've been throwing around some words here. You have to know the difference of them. Resolution is the ability to distinguish between 2 points. Our scope's guaranteed to do 5 nanometers. Depth of field is a region of acceptable focus. This is fairly subjective. Aperture is a physical opening or exit pupil. Basically, it's a hole. F-stop is a ratio. The higher the f-stop, the smaller the aperture. The smaller the aperture, the better the depth of field is. Magnification is a field of view. The electron microscope doesn't physically increase the size of something. It just changes the field of view when you dial up the magnification. And astigmatism is a hard stop. It's a distortion caused by imperfect lenses grinding non-perfect lens shapes. Aperture and focal length. This is the Nikon 80-200. It's a $1,200 lens. It's a 2.8 aperture lens from 80 to 200, or you can dial it down to f/22. The smaller the f-stop, the more light it lets in. The more expensive the lenses, the more light it lets in, and the more high quality the image is. On a cell phone, it's maybe f/11. Basically, it's a pinhole. That's why all your images come out sharp all the time. When you get into this high-end glass, the lower the f-stop, the more expensive. What does it subjectively give you? At a wide open aperture, the depth of field is very, very narrow. If you look at a picture of my son here, see the brim of his hat's in perfect focus. Everything before and ahead of it's a blur. If the electron microscope had these optical qualities, these images would be no good. If you're at a point where your aperture allows you depth of field and everything else, and resolution, this is pretty much a hyperfocal point. This is basically the infinity setting on the glass. That's why when I took a picture of this airplane, everything's in focus from the tip of the wing all the way back. If you look at it, the resolution is a little poor. If you look on the inside of the stabilizer, you can't read the numbers or the insignia. So the lens is extremely sharp, but sometimes other factors go out the door. This is done on the 80 to 200, which is a $1,200 lens. This image I just put up to show you with photography, it's all about being there. It's all about being in the moment of time. It's the same thing on an electron microscope. Once the sample's out of the chamber, if I didn't image it, it's very hard to go back and redo it. This is a condensation cloud. Technically, it's the Brandel singularity. The plane is not breaking. Basically, it's flying so fast, it's compressing the water vapor into a vapor cloud. The shape of the singularity strictly depends on the airframe design. Different airplanes give different condensation patterns. Basically, it looks like it's flying out of a hole in space. It's pretty neat how it works. But anytime the transonic on a humid day, you'll see that vapor cloud, that shock wave being formed. And depending on what the perspective is either the front or the rear of the aircraft. People tend to equate word poor resolution, high resolution, and think field of view. The reason why I put this picture up is, how we talked about the fact that the instrument's idiot-proof of all the push buttons. The reason why this airplane crashed is because the computer system didn't have the ability to make note that a very simple setting was wrong. This is an Air Force Thunderbird. Anyone who flies an airplane knows that on the altimeter you have to manually set the pressure altitude. Well, this pilot went to the air show before, set it for a certain altitude, went to a different elevation air show. He didn't change the altimeter setting, so all of his computers and all of his instruments were telling me he was flying 1,000 feet higher than he actually was. When he went to do this maneuver, he physically did not have enough altitude to complete it, so he had to eject. This is not a mechanical failure. This is a pilot error. Even with all the fly-by-wire advanced avionics, if you do not manually set the right altitude, everything's screwed from there. It's the same thing on that electron microscope. If you make a critical assumption and do not set certain things a certain way, no matter what push buttons and auto settings you have, will not save the day. This is an image of poor resolution, even though this is probably taken on a $14,000 lens. What I mean by poor resolution is if you look at the cars in the parking lot, see how the whole image appears to be a blurb of cars. On a high resolution optical system, you'll be able to distinguish the car and the space between them. Everything's not just blended into a mash. Like here, I can't tell where this car is separate from this red truck. That's resolution. On the electron microscope, if each one of these cars were 5 nanometers apart, you'd be able to see that separation. So this, even though it's a high impact image, it's a high quality zoom lens, you get depth of field, there's no color fringing, there is some image compression, but the resolution is not the best on this lens. Okay, when you get into the electron microscope, you're dealing with a pinhole that's been laser drilled into a piece of metal. These pinholes these apertures are replaceable. If you want to hear more about the pinhole photography, you can go to my website. I modified a disposable camera where you can do pinhole imaging. This is physical optics here, folks. The hole I drilled is 0.3 millimeters. My f-stop is f75, so you pretty much have infinite depth of field. If you want, I'll give you a little homework assignment. If someone could tell me why This light coming through the window is white and has a purple tinge to it. You can just Facebook me with an answer, which I already know. That's an FYI for the scientifically curious. I didn't modify this image. I'm not shining an LED flashlight in the background or anything. This is natural sunlight coming through a shack window. But if you notice, it does have a purple tinge. Okay, how does the electron microscope generate an image? Everything's done in the digital domain. Back in the old days, I used to use film plates, but nowadays, those are long gone. To understand how a digital image works, you gotta understand the principle of the histogram. Everything on an electron microscope is black and white. Basically, in any image you take, you'll notice that you have different shades of gray, going from black, which is 0, all the way up to white, which is given a value of 255. In this picture here, you have roughly 1, 2, 3, 4, maybe 5 different shades of gray. In the histogram, almost every digital camera will give you this. Ignore the fact I'm going from black and white to RGB. Basically, the way it works is this peak here is the darkest image here, which would be the trees. The gray clouds would be these dark gray. The medium gray would be some of the lighter shades, or maybe the water. And the bright clouds is stuff that's expressed in white, is shifted far to the right. So if this was an electron microscope image, it would show you 1, 2, 3, 4, 5 shades of gray. It's very important that once you get to backscatter images, so if this is wrong, everything else you infer is wrong. The way it is, the microscope has a processing algorithm, and it assigns different backscatter signals different shades of gray. On the periodic table, there are 92 natural elements. So if I had a 92 element mix and I wanted to look at it and display an image, it would display it as 92 different shades of gray with anything between. To get 92 shades, if I use an 8-bit CPU, it's 2 to the 8th power. In theory, I can show 256 shades of gray. So just simple 8-bit DSPs are enough to be used in the circuit of this microscope. What's important about it are the two things here in green. If I'm looking at a backscatter image, if I see 3 different shades, or if I'm looking at the raw histogram, if I see 3 peaks, it is inferred that there are 3 different areas of chemical composition in it. Now, if the histogram is clipped or for any reason wrong information can be deduced is very critical. Focus and the resolution is independent of the histogram. I'll show you what I mean by this. Most people, when they run the electron microscope, they click the auto function in, and they hit image and they hit save. If this is messed up for any reason, your scientific results can possibly be thrown out the door. Again, this is this fast and easy and cheap philosophy I'm hearing with the COVID. You got to take your time on this stuff, folks. Same thing for the electron microscope. You got to take your time on it. Typically in the past, when people tried to do any work in the lab, they looked at it as a drop and run facility. You drop it in, 5 seconds later, you get a research quality publication out of it. That's not the way it works. I used to get a lot of looks when I tell my students, I need this sample for a week. Or if you want this done right, it's going to take me a month to do. There's something fast and easy about science. Okay, the ideal histogram in an imperfect world. Now, when it pertains to the electron microscope, anytime you see an extremely black grayscale on an image, it's pretty much these 3 elements: boron, carbon, nitrogen, and oxygen. These are very low atomic number, poor backscatter signal. The middle section of the periodic table, it may be light to middle gray. The right side of the axis is white. These are the D and the F block, which is the transition elements at the bottom of the chart, i.e. stuff we use for catalysts and stuff. Anytime you move left to right, atomic number increases. If I tell you that the white part of that image is boron and the black part of that image is platinum, you better be running for the door, because The lighter elements are coated black. The whiter shades are the heavier ones with the higher atomic number. So if my histogram is overexposed, I may come to that conclusion. In a perfect world, you want perfectly Gaussian peaks. So it's not always the case. That's why when you look at the histogram, it's not a perfect Gaussian. This is what the microscope software gives you. It gives you an image. It gives you a visual picture of the sample holder. We're on step 1. Basically, you turn on the beam, you hit run, it generates an image in a few seconds, and you can hit save and print. That's what the amateur does. They click on the auto line, and you hope for the best. What I do is I always keep the histogram window open, and I look at it. Anytime I have an image that's overly dark, it could be because of 2 reasons. Either these settings are wrong, or the brightness and contrast controls are wrong. These are set of knobs on the console. Ideally, what you want to do is you want to get whatever histogram you have centered or to the right 2/3 of the graph here. So this whole section here has to be moved over here. Now, if I were just to click save and print and give this to a professor, he's going to go, okay, I gave you a sample that only had 2 different elements in it. Why am I seeing a black, a gray, and extremely bright here? That's telling me there are three elements here. If you didn't know that the histogram was wrong, you would not have an answer for him, and he's highly unlikely to use your lab or your skill set to do science. Because what this is telling me is that the background here is the carbon tape, but these crystals are the catalyst, and the white spots should be the transition metals that are deposited on the catalyst. But he doesn't have a catalyst that has transition metals on it. This is wastewater flock. These are very low Z elements here. Phosphorus, sulfur, magnesium. So something's wrong here. Okay? The reason why it's so bright is because this spectrum's clipped. So you can be underexposed, or you can be overexposed. This one's more hard to work with than underexposed on a microscope. Pretty much here, all you gotta do is back down the brightness and contrast, and then you end up with this image, which is the correct exposure. Basically now, what's happening here is I'm at 15,000 volts. So when the beam comes in, it's really lighting up these samples here. So it's giving a pretty strong backscatter. The background's the tape. Pretty much everything else is the same shade of grade, so it all has the same chemical composition. But there are a few flecks of the wastewater contaminants that are filtered out. That's what these single white spots are. I would have to coat the sample to get rid of the charging. But just by looking at the histogram, I know So I'm pretty sure that this image is a good one compared to this one or that one. Summer, then we're going to go on to looking at actual images. You can use the brightness and contrast controls to adjust the histogram. The image does not have to be in focused. You want it centered in the right 2/3. But this applies for any computer editing or camera work. All cameras now have a live histogram. Most people don't know what it's for or use it, but you have to know to get quality images. You have to know how to do this. The key takeaway here is that this does not improve the image of the histogram. Your last option is to change those probe and beam conditions. It requires a serious scientific thought and process. If you just clicked auto align and auto adjust, you don't get that skill set. That's why all my grad students had a real hard time generating a research quality image on something that was publishable. They just don't want to take the time to learn the system and learn how to do it manually. Okay. If I'm going too fast, you can always go back, hit pause, and look at these slides. If you have a question, feel free to FaceTime me or Facebook me. Okay, images. This is the fun part. This is a plant leaf that I took from outside, put it on the microscope. This is a secondary electron image. basically it's charging up the sample, and it's just repelling the electron beam. That's why it's got this spotlight effect where it looks like it's being hit by a floodlight. This image is not usable, period. The electron microscope gives you infinite depth of field. This is a micromilling drill bit that's being studied for wear abrasion. I'm a co-author on this publication. If you Google Scholar Me, how the drill bit's already being chipped. The black stuff is oxidation and part of the material that was drilled to. This is a coated drill bit. It's got a boron carbide or nitride coating. You can see it on the outside. See the dark gray on that. That's a backscatter image. Boron's and carbon's a low atomic number. The drill bit's a mellow alloy. It's a high Z element. That's why it's shaded in. So basically this thing has two phases. You have the coating and you have the actual metal of the drill bit. If you look at it, you can see the machining marks on it, and you can see all the way down the drill bit. You can even see the sample holder in focus. The key thing to note here is I'm only magnifying it 150 times. This is an optical microscope range. I can go to Costco and buy a toy microscope and magnify this image. Key takeaways: acceleration voltage is how much energy I'm using to generate the image. 21 millimeters is the distance from the end of the microscope to the top of that drill bit. You have the magnification, which is the field of view. Backscatter is the mode. And the scale bar from here to here is 300 microns. I'm sorry, yeah, microns. It's 300 milliliters of a meter. So roughly this drill bit is 300 microns across. The whole image is about 300, 600, 900. Half of this bar is 150, another half is 75. Milli is millionth of a meter. In the backscatter mode, I can look at a defect. Here it's doing a line scan of this image. You can see this little crack or channel, which is represented here in the line scan. Again, you can see the difference in the grayscales. You got the coating, and you got the actual metal of the drill bit. Then you got the carbonized deposits on top, and you can see them. They match up perfectly. And there's a scale bar, and you can do a 3D rotation of this image in the software. It's pretty cool. It gives you the topo data. And here's some of the forensics work. Here I put my fingerprint onto a glass side, and I coated it with gold. I'm imaging it at 5,000 electron volts, which is not real strong. I'm magnifying only 20 times. It's a secondary electron image. And this whole scale bar is 2 millimeters, millionths of a meter. But you can see the whirl of my fingerprint. You can see some carbon contamination. Basically, when you touch the slide, you're inputting a biofilm of your skin oil. Then when you coat that, that's what it's imaging. Much luck with the backscatter because the slide is all lightweight elements, and the oils on my finger are lightweight elements, so pretty much this whole image is going to come out gray. The secondary emission mode is good for this. You can do failure analysis of metals. This is a piece of steel that structurally failed. This is hydrogen embrittlement. It's a secondary electron image. You can see all the surface defects. You can see the boundary grains. You can see the depth of field is pretty amazing on it. To the naked eye, the steel seems to be perfectly fine. It's shiny, it's mirror flat, but under the microscope you can see the internal damage. Normally when steel fails, it bends. This sample just snapped. It looked like somebody made it out of plastic and just twisted it and snapped it. It's hydrogen embrittlement. When it hits a certain structural failure point, it just goes. Here's another picture of that same piece of steel. It's only magnified 500 times. It's on a micron scale. This is a good example of the hydrogen embrittlement. This is the outside surface of the piece after it's been polished and cut. You can see the grain boundaries. You can see this huge divot. It's hydrogen embrittlement. What happens is when you weld or manufacture steel or use steel, if it's high carbon steel, some hydrogen will diffuse into the steel. The hydrogen reacts with the carbon in the steel, forms methane. Eventually the methane starts to expand and pop, and a bubble pops. It induces these cracks and failures inside the material. Then the cracks start to grow, and eventually the whole material will fail. That's why they do welding in inert atmosphere. It's also why at the refinery they're always swapping out valves and parts. When you're dealing with high pressure oxygen, the hydrogen embrittlement process really accelerates. These are some copper nanowires. Even at 500 times, I can see the nanowires in the image. It's backscatter. Basically, it's a copper oxide crystal with some nanowires that have grown. I'm not going to discuss the process. You can look it up in one of our publications. But you get these nanowires. So even at low magnification, it's possible to get a high resolution image. This whole section here is 100 millionths of a meter. Now if I magnify up, I can see truly how fine these wires are. The background is the carbon tape. That's the copper oxide crystal, and these are the nanowires that are growing out. This whole section is 10 millionths of a meter. So these are pretty small. These are pretty small. These are the nanowires at even a higher magnification. Again, you may be asking, why is it a little fuzzy? It's because, number one, vibration. Not all these fibers are physically attached to the sticky carbon tape, so they move around under high vacuum. You got that magnetic field interference, RF noise, people walking down the hallway, truck rumbling down the road. The aperture is not perfectly centered. You're using a $100,000 tungsten filament microscope when you should be using a cold field emission gun, which is about a half a mil. So, it's price performance. But again, the researcher can see the fibers, he can measure how thick they are, he can see they're very consistent on structure. Now if I spend a lot of time fine-tuning this or mounting it a little better, I can get it a little sharper. Here are some nylon fibers that were spun. Here I'm at 100,000 times. Here we're at the nanometer scale. From here to here is 500 billionths of a meter. So this fiber is under 100 billionths of a meter in diameter. It's pretty much the same diameter, and it's the same structure. And we'll take a little break here and throw in a little discussion on PPE. On the internet here, there's a whole bunch of talk about why do I need to wear a face mask, or I'm going to be an idiot and not wear one, or how does it stop a virus, how doesn't it stop a virus. People, what you got to understand is, even if you go to the store and buy a NIOSH approved N95 respirator, these respirators are designed for paint fumes, welding particles, dust. They're not really designed for stopping viruses. Okay. The N95 means that it stops 95% of fibers, particles that are larger than 300 nanometers, which is 0.3 microns. Your average dry virus is somewhere between 50 and 150 nanometers. It's small enough to get through the pores of that filter. Now the odds of a dry viron perfectly lining up and going through that filter, slim and none, but the chances are. No PPE, I stress this a lot when I did industrial hygiene, is guaranteed. If you don't wear it properly, you must not wear it at all. And when I walk around and see these images, half these clowns aren't wearing it properly. You're making it yourself with no quality control. It's not a NIOSH traceable filter. So yes, there is some risk, but some PPE is better than no PPE. And that's what these clowns don't understand when they refuse to wear one. Even when I was at the plant and fitted someone for a full face respirator to go into a toxic, potentially lethal environment, there's always a chance that the fit's not right. They're not wearing it properly. They're just being dumbass or stubborn headed, and bad things can happen. It's the same thing. You're better off wearing a mask than not wearing a mask. But you have to understand that just wearing the mask does not automatically guarantee you that you will not be exposed to or transmit the virus. But if you look at China, the ones that where they wear the mask, it keeps people that are sick from getting other people sick. It doesn't totally block cough droplets and aerosols from getting out, but it does do a significant reduction. So grow up, people, man up and wear the mask, or don't go to the store. Now, if you have trouble breathing, if you have respiratory problems, I can understand you not wearing a mask. But you got to start thinking of others. Because if I were to take a TEM of that COVID and put it, it would fit inside that fiber. It might not fit through that gap, might not fit through this gap, but it will fit inside the diameter of this fiber. These viruses are very, very small when they're dry. Now, when it's a micelle with a mucus or water droplet, it's fairly large, and the N95 will stop it. But if you happen to expel a dry virus, it's going to go straight through that filter, or possibly go straight through that filter. And here's some more images of the electrospinning. See how they're all uniform in size. Here's some fibers that are spun to be parallel. The white spots are salt contamination from the sample not being washed. And there's some catalyst on there. The more they wash the material, these spots go away. If you notice, it's all one shade of gray. It's very homogeneous in its composition. But you can see the surface contamination. It has to be washed off. See how it has like a rope look to it? It's not perfectly round. This is a high resolution image. Same thing. The background's the matrix that the fibers are being spun out of. This was an imperfect spin. That's why you don't see all fibers. So these conditions on electrospinning are no good for this material. Some of the neat stuff you can do with electrospinning is you can make a fiber that's porous. There's a lot of talk about using these for nanobot or drug implants. In theory, you can put a drug on a nanoparticle, put it inside of this fiber, implant this in the body. When the body degrades the fiber, the drug gets released, or the nanoparticle gets released. The bright spots are the nanoparticles that are deposited inside this polymethyl methacrylate fiber. If you notice, this kind of fiber is porous. All these holes are roughly the same size. It's a backscatter image. These are carbon nanotubes, polypropylene. If I had a TEM, or if I had an instrument that had a field emission gun, you would see these as individual fibers, but that's one of the limitations of the tungsten filament that's in this microscope. It's also why the price is $100 grand, not $1 million. This is a commercial carbon nanotube that was bought. These are the grain boundaries in an ASTM steel alloy. You can see the oxidation carbon deposit. It's a secondary image, so you can see the surface features well. See, even after cleaning, it's still dirty. It still has some carbon deposited on it. Here's the yellow pollen that coats everything in Beaumont, Texas during certain times of the year. You can sort of understand why the pollen's an allergy. It's got these very, very sharp ridges and protrusions on it. You can just imagine when that gets in the lungs of the nasal cavity, you can't be near it. These are actual aerosol droplets. Down here we have pollution problems from our local petrochemical money mills. The air was so bad, If you had to go to sleep at night, you had to put a wet rag over your mouth and nose so your eyes and nose doesn't burn from the sulfuric acid coming out of the stacks. Now that's gotten a lot better, but it's still present in the air. When I was working on my master's, we did a lot of work with the PM 2.5 and aerosols. So here I'm analyzing some unknown material on a sampling filter. The material is actually it's sulfate from sulfuric acid. If I run the EDAX, all it shows is sulfur and oxygen for these droplets. I did coat this. These aerosol droplets are physically bound to the substrate. Even under high vacuum, that they don't outgas or evaporate. Okay, what's the highest you can magnify and resolve on this instrument? The instrument will go from 0 to 300,000. But this is just a field of view. Magnification is just a scanning area ratio with scanning speed. You either have a big number on top or you have a big number on bottom. It doesn't physically enlarge the material. It just changes the field of view. That's one of the assumptions is people run to the lab. Well, I heard your microscope will do 5 nanometers. I want to see my image multiplied at 100,000 times. Each material has its limits on how high you can magnify. Hitachi professionally prepares a gold target. It looks like a little gold coating on a stub, but under the microscope you can see the growth plateaus of these deposited gold atoms. So you see these clusters of gold. If I take a look at it from here to here is 500 nanometers. If I measure the distance between these smaller gaps, you'll see 5 nanometers, 10 nanometers. So the microscope does do the resolution of 5 nanometers, but you have to have a certain sample to do it. You just can't put anything in there and see 5 nanometers. That's why a lot of times these guys will come to my lab and they'll bring me stuff in a glass tube and they'll shake it up for me, and I can hear the stuff rattling around inside, and they go, "Oh, the stuff's on the 1 nanometer scale," and I'm going, "No, you're nowhere near it," because I can hear it rattling around in the glass. So you gotta be real careful when you read up on all this new science, because all the funding in science goes for quote nanotech. So you have a lot of people that are dabbling in nanoscience that really aren't. Because if it were to be nano size, I wouldn't hear it rattling around in that jar. And of course, when you put it on the microscope, there are no nano size features on it. I mean, in theory, I could grind it up in a ball mill and get it extremely small, but you know, some of this just isn't nanoscience. Some of the more cool stuff you can look at. This is a fire ant head. This whole thing is 500 microns. I'm only magnifying 80 times. What I did was I coated the ant gold, stuck it to the tape. You can see the hairs. You can see the eye. You can see the legs. You can see the mandible. This is how they bite and inject venom. I think a fire ant stings and injects venom. It does it in a dual mode. But if you look at the depth of field, the mandible is sticking right out at you. And I have an image of the teeth here. I'll show you. You can see the detail in the arm hair, the pores. You can see the follicle, the compound eye. You just can't do this with a regular microscope. I prepared the sample in probably 5 minutes. Okay. These are the hairs on the legs. This is the mandible. The SE image is a little out of focus. This thing is sticking up pretty far out, so the depth of field is beyond the range of it. That's the arm and the leg. Go into the socket. See the hairs? This is a backscatter image. You can see the teeth. If you wear 3D glasses, if you did a 3D mode, you can look at this in 3D. This is the photonegative imaging mode of that same image. It looks like some alien. Again, like I said, all these images I've shown you in today's presentation. This is the last one. It's a mold spore. Different science experiment for my son. It's a penicillin spore. Mycelium body behind it. All this stuff is in a public domain. If you click on my Google Scholar link, you can look at these publications. I didn't include any research that wasn't published or publicly available. None of it's classified or patented, and even then, I'm not giving you any real technical details on the images, so don't email me or Facebook me and ask me. But again, like I said, nothing's out of any projects that were classified or anyone's work at the school. A lot of the stuff is just mine or stuff that I pulled out of the cabinet from people's old samples that they left behind that didn't have any use. Again, you can go back to my publications and see more of them. Okay, that's it for the electron microscope. I'm going to prepare one for the XRD. If I'm unclear on anything, if you want more details, Facebook me. I try to keep all politics and religion off my site. Everything here is based on science. When I talk about the COVID, my little rant on wearing PPE is based on my scientific experiments. Remember, some is better than none, but you still have to wear it properly. And you need to be extra worried when you make your own mask because there is no quality control, whereas if you buy one, there is. And just remember that this virus is extremely small, and that's one of the problems they have with stopping it. 100 nanometers is 100 nanometers. We will get back to you in a little bit.